Here I want to do some things with power series that we haven't explicitly discussed. I've discussed a little bit of integration before. I haven't really done anything else with it. So let me just start with an example of what I'm talking about. We know that the sine, I'm going to use theta because I'm going to use x later. The formula for sine of theta looks like this. Theta minus theta to the third over 3 factorial plus theta to the fifth over 5 factorial minus theta to the 7th over 7 factorial, and that goes on and on. So imagine you're confronted with a limit like this. X times sine of 1 over x. I'll show you an alternative way that's very simple to do this in a minute, but let's just say you're stuck and you really have no idea where to even start this. Like you don't know how to make it into L'Hopital, whatever. I've actually had a limit or two in my life where I had to revert to a power series to get the answer that I wanted. So anyways, what we're going to do is I'm going to use this series, but I'm going to plug 1 over x in for theta. So this will be the limit as x goes to infinity. For right now, let me keep this x here outside and then put in the series for 1 over x. So the first piece will be a 1 over x. And then this piece will be minus 1 over x cubed, 3 factorial times x cubed. And then I'm going to have plus 1 over 5 factorial times x to the fifth minus 1 over 7 factorial x to the 7th, and this goes on. Alright, so then what I'm going to do is multiply through by x, and I will get 1 minus 1 over 3 factorial x squared plus 1 over 5 factorial x to the fourth minus 1 over 7 factorial x to the sixth. Well, as you let x go to infinity, 1 is unaffected by that stuff. However, since x is in the denominator of each of these, each piece is going to 0. I'll just put this so it mimics the series. And you trust that this series converges because sine, and in fact it doesn't matter as long as x doesn't actually equal 0, sine this series is defined for all real numbers. And it ends up equaling 1. So if you're stuck, you can come up with something like that. Alternatively, you could have realized it this way. I could have rewritten it as sine of 1 over x divided by 1 over x. And here what you have is sine of something going to 0 and the denominator going to 0. You can use L'Hopital's rule, but we already are supposed to know this one. We know that the limit as theta goes to 0, sine of theta over theta equals 1. In fact, it's the first, probably the first limit that's actually done where they had to use the squeeze theorem to get the answer. Another series, I don't know if I've done it explicitly, but the cosine series works like this. It's exactly the missing terms, like sine and cosine together would form a series where every term would be there, even and odd. But here, cosine is by now well known to be an even function. I'm avoiding sigma notation because it just makes things cumbersome. And suppose I take the derivative. I do it to the other side. Just do enough terms so you get the idea. Of course, the derivative of 1 is 0. Then I'm going to get negative 2x over 2 factorial plus 4x cubed over 4 factorial minus 6x to the 5th over 6 factorial. I'll do one more just in case it's not evident to everybody just yet. So 8x to the 7th over 8 factorial minus dot dot dot. With a little simplifying, I get negative x. This 4 cancels with 4 factorial, leaving 3 factorial. So you get plus x cubed over 3 factorial minus x to the 5th over 5 factorial plus x to the 7th over 7 factorial minus, and that will go on. Next I will factor out a negative. And hopefully you recognize this series, all odd powers like this, the denominators are working just perfectly to give us negative sine of x. So the series, obviously since the series works for cosine of x, all the derivatives and things like that should give the same answers as before. Alright, for this one, I want you to find a formula for the following series. 1 plus 2x plus 3x squared plus 4x cubed plus 5x to the 4th plus. Now the idea is for you to look at this and say, well, I see that this is almost a series I'm familiar with. If you'll notice here, look at this 2x. If I integrate it, I can get an x squared. If I integrate it, I can get an x cubed. If I integrate it, I can get an x to the 4th. Anyways, this looks like something that has been integrated. So if I integrate it, I'll figure out the limits later on, but I'll get 1 plus 2x plus 3x squared plus 4x cubed plus dot 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 dx all the way out there. What will this equal? X plus, and then we'll have x squared over 2, we'll make that x squared, plus, and then I'll get x cubed, plus, and then I'll get x to the 4th, plus, dot, dot, dot. It goes on forever and ever and ever. Then, of course, I can factor out an x. And I'll get 1 plus x squared plus x cubed plus dot, 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 dot. And this series, you should write, this is the geometric series with base x. And of course, if I want a closed formula for this thing then, this will equal x times, we know the formula for that thing is 1 over 1 minus x. So what I have then is x times 1 minus x equals the integrated version of the series. So x over 1 minus x. And here I'm going to use c is equal to 0. I'm just looking for formulas here. I'm not exactly finding a solution to a problem where I'd need to plug anything in. So I have x times 1 over 1 minus x is equal to the integrated version of that. So if I want to get back to the thing I was supposed to be finding a formula for, I can take the derivative of it. And that will give me the original series back. That's why I didn't bother with the constant. It's going to disappear at this stage anyways. And then over here you can use the quotient rule. So 1 times 1 minus x times negative 1 all over 1 minus x squared equals 1 plus 2x plus 3x squared plus 4x cubed plus dot 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 dot. And then we have 1 minus x plus x. So I'll get 1 over 1 minus x, the quantity squared, equals this series. Now, I think that I will go and put it into a summation formula. So anytime you start at 1, I could do, looks like we're going to have 2. If I start at 0, can I do, then this would be 1. So this is like k plus 1. Let's see what happens if I do this. When k is equal to 0, I'll get 1x to the 0. That'll give me the 1. When k is equal to 1, I'll get 2x to the 1. Then when k is equal to 2, I'll get 3. All right, so it seems to work out. So whatever the case, this is the guy you were looking for. So you can differentiate or integrate. Many times you'll look at them and you'll see that they have, you'll spot something that is almost a series. Like I noticed up here, I go, this would have been nice if this would have been integrated, because then it would follow the geometric series. So a lot of them, if you have handy a collection of formulas for the main functions that we're dealing with, a lot of times you'll look at a series and you'll be able to do some manipulations like integration, differentiation, or even something else to appeal to the series you know. And here's a good question too. Check out these. Take a look at this series, ck x minus a to the k. The differentiated version of the series will look like k ck x minus a to the k minus 1. Now, when you go and do the ratio test on that, on the first series, look what you get. The ratio test will give me, for this particular series here, you would do the limit as k goes to infinity, and you would remember to do the absolute value because you're talking about setting this whole thing less than 1. I'll get ck plus 1 times x minus a to the k plus 1 all over c sub k x minus a to the k, and that will equal, what I'm going to do is divide these up. This will equal the limit as k goes to infinity. I'll have ck plus 1 over ck times x minus a. And many times we'll set that less than 1. I'm not going to go through a lot of all the ugly, horrible details, but this stuff right here, this guy right here, when it's not 0 or infinity, that thing there is 1 over r. Because the first thing you do is divide by that thing, whatever it turns out to be, and that tells you what r is. So now look at this one. This is the differentiated version of the same thing. So I'll do the limit, k goes to infinity, and I'll have k plus 1 times c sub k plus 1 x minus a to the k all over k ck x minus a to the k minus 1. Now let's do some simplifying as before. I'll cancel out the x minus a's, and I will get the limit as k goes to infinity, k plus 1 over k. I'm going to separate that. C sub k plus 1 over c sub k, and then the absolute value of x minus a. Well, this limit is 1. You can break this into individual limits, assuming all of them exist. This thing is going to be 1. So I will get the limit as k goes to infinity, absolute of ck plus 1 over c sub k times the absolute value of x minus a. And if you look, there it is again, 1 over r. So if you look at these two things, both of them have the same radius of convergence. Now, there's always endpoints to check, but they both have the same radius of convergence. That means, let's go back to this here. The radius of convergence of the series, of this series right here, is between -1 to 1. That automatically means that this series will converge for -1 to 1. It may or may not converge at the endpoints, but it has the same radius of convergence. Likewise, so does the integral. So this is a nice thing to work with, knowing that no matter how many times you differentiate or integrate, you're still dealing with generally the same interval of convergence, just the interior of it, which would be the open interval and not necessarily closed at either of the ends. Here's an interesting application. Try this one. Now, calculators can give an answer to this, no problem, but you won't be able to integrate this by hand. It is known that there's no antiderivative. How do I put it? There's no closed form antiderivative for e to the -x squared. This has actually been it's proven. You can't try as you might. It's actually proven that there's no closed form for this solution. That means whatever you do is going to have to involve a series for it. So if I wanted to integrate something like this, I recall that the formula for e to the x equals the summation k equals 0 to infinity x to the k over k factorial. This is one of the most important of all the series that you know. It could be described as the most important one because a lot of secrets are hidden within this particular series. It's a very powerful series. And you should try, take the derivative of e to the x, which you know to be e to the x, but do it to this series with a little simplifying. You'll see that you get the same series back again. So e to the x is a very powerful series for that. Anyways, if I instead replace x with -x squared, this is what I'll get. I'll get the integral from 0 to 1. Let me just take this and keep it from bothering me. I'll have e to the -x squared dx equals, and I'll replace it with the sum, k equals 0 to infinity, -x squared to the k all over k factorial dx. Now, you can't integrate term by term. You're just going to have to take my word for it. The reasonings why are, it's complicated. There's the topics involved in proving that that's true are advanced calculus topics. I don't mean advanced placement calculus. I'm talking about advanced calculus, which deals with proving all of these theorems that we throw around in rigorous detail. Anyway, so what I'm going to do is this. Let me go ahead and simplify that a little bit. So I'll get -1 to the k, x to the 2k, all over k factorial dx. Now the leap of faith that you're going to have to make with me comes at the next step. I may integrate this term by term. And the reasonings why involve topics that I cannot divulge right now. I'm not at liberty, that's not true. I am at liberty to say, but they will just be ridiculously complicated for you, and it will go way beyond topic. But rest assured I can do all this stuff. And the reason why I want to go through this level of detail is right now, here you've got an infinite sum. In some ways, an integral is an infinite sum. If you think about it, when you think about the Riemann sum and all that kind of stuff. But look at this integral. The thing that is being integrated is with respect to x. That means if something doesn't have an x in it, this integral thinks it's a constant. So I can rewrite this as the sum, k equals 0 to infinity, the integral from 0 to 1. Oops, I didn't mean to do that. I want to pull out the negative 1 to the k over k factorial, and then perform the integration on simply x to the 2k. And that's a really easy one. That's the beauty of these series. Everything is a very long polynomial. So all those things with polynomials, true polynomials being the best of all possible functions that can possibly exist. So when I do this integration, then I'm going to get x to the 2k plus 1 all over 2k plus 1. And that'll go from 0 to 1. Then I'm going to get the sum k equals 0 to infinity, negative 1 to the k over k factorial. And then when I plug in 1, I'll get 1 to the 2k plus 1 over 2k plus 1. But then when you plug in 0, you'll get 0. So this is it. This is the final series. Let me go ahead and write it in perhaps a simpler form. Now, this is the thing. We can evaluate this for different numbers. Instead of going to infinity, go up to, say, n. And I'm here to show you how to get your calculator to give you some values for something like this. So let's go ahead and throw it. Let me put that way up there so it won't block the calculator view. Let me move it over to the side and turn it on. Try, okay. I am going to get out of that. I don't know why I was in there. Clear the screen. And now what I'm looking for is to sum a bunch of things. So what we can do is go to second and go to your catalog. Just like before, look for the first letter that you're looking to look for things, and I'm going to use the letter S for sum. So it takes me to these things, sample, test, psi. Just scroll down and you'll get to it eventually. Up there it was. Gotcha. Now, when you have a sum, you've got to tell it the sequence that you're going to be using. And the sequence we're using are these individual terms. So you've got to tell it to sum a sequence. So I'm going to go back to the catalog, and I'm going to press the letter S again. Scroll down. There it is. SEQ with parenthesis around it. So I got sum, seq. Now this is what I want to put in here. So what we'll do is parenthesis, oops, negative, was it negative 1 to the k? I need parentheses around it. Negative 1 to the, now here's a problem. Did you see what it did? It put an x instead of a k or an n, which I think you're allowed to do this. Let me just continue. I don't know if I have to change the mode or not, but then I'm going to divide. I want to encase the denominator in parentheses. So I'm going to have my k factorial. So in this case, I'm going to use x. And remember where factorial is in the math. Go to PRB, choose number 4. Now then I have to multiply that by 2x. I did not mean that as my x. I meant 2x plus 1. Now this one line input stuff is very annoying. I got to remember to finish off the 2x plus 1. Then I have to remember to finish off the parenthesis. Now, I believe you can put what thing is going to be used as the variable here. Well, tell it x. I think you'll be okay here. Comma. Where does it start? 0. How high do you want to go? I'll start with 10. End the parenthesis. I think I have enough of them, and let's see what happens. So what I have is 0.7468 sum k equals 0 to 10, negative 1 to the k all over 2k plus 1 times k factorial. And since I'm estimating to 4 places, I'll just put squiggle lines, and my number is 0.7468. So 0.7468. Now let me go up to 20. This is an annoying thing to put into the calculator, especially since it's all in one line, and this doesn't have to be like that. What you can do is the following. Bring your calculator back, go to second, and above enter there's something called entry. It will allow you to it'll put your last entry up before you, and then you can go back and edit the 10 and change it to a 20, and then hit enter. And you can see to 4 decimal places, wow, look at that, to 4 decimal places, I don't just have, I mean, this is almost all the way to 10 decimal places, so I feel really good about these. 10 or 20 gives me practically the same thing, so 0.7468, I mean, they're so similar that I can say without much feeling of fear, this guy right here is approximately equal to 0.7468. So you can do a lot of things. You can estimate values of e. Remember, e to the x equals summation k equals 0 to infinity, x to the k over k factorial. So if you wanted like e to the 10, you could use this series. So that'd be 10 to the k over k factorial. And then you could put different values up here, throw it in the calculator, see what your numbers that you get. I know you can do e to the 10 directly, but nonetheless, there are times, I'm telling you right now, when you're going to do programming, which I'm assuming most of you will be in some sort of a technical field since you're in calculus 2, but if you're going to do some sort of programming, it's oftentimes that I'll have to work with things, that I have had to work with things that didn't have an explicit representation in the computer for it. So I had to do something like this, and you can do it recursively. You can let x equal the 0th term, and then you go, if x is less than something, then, and then you go, and then you reset x to be like x equals x plus 1, or x plus the previous term, or something along those lines, and then you get sums. So, and these are what are used in science. They oftentimes do not have exact answers for anything. They have to use infinite series many times to estimate things. Now, this part, I don't think I'm not requiring it to be known how to do, but I think it's important. Through all the things we've done, we have made, I've said this oftentimes, or there's one for sine or tangent or whatever. What happens here is we lose track of the fact that when we developed the series for these things, we simply made sure that the series had the same derivatives at a of the original function. There's nothing in any of the theory that we've done that actually says that the series fills in the gaps between the derivatives or at other values. So how do we know this is exactly true? How do we know this is an exact answer? By the way, the interval of convergence is negative infinity to infinity. That means this works for any value of x. How do we know that actually works? And there was a very slick argument given by the authors of our current textbook. I'll just take Briggs-Cochran, section 9.1, exercise number 92. They step you through it, and it's a really, really slick way of developing the series and showing you that they are equal to each other. To me, this derivation and proof is rather ingenious, and it uses only ideas that you've encountered. Nothing advanced is required here. So I'll make a note when something has to be finite or something can't be 0, something like that. But for the time being, let's recall the following fundamental theorem of calculus. And you know that if I have an integral from a to b, f prime of t dt equals f of b minus f of a. The integral undoes the derivative. So with that in mind, I can do the integral from a x. Now I'm going to let the top limit be variable. However, I'm going to fix x throughout the rest of this problem because x is going to be just a number. So I can do the same thing, f prime of t dt, that will equal f of x minus f of a. So I can rewrite the function f of x. Just add f of a to both sides to get f of a plus the integral from a to x f prime of t dt. Now, instead of just integrating straightforward, I'm going to use integration by parts. So we're going to go integration by parts. And I'm going to let u be f prime of t. Now I'm operating with the variable t, so du will equal f double prime of t dt. And then dv will be what's left over, which is dt, just that part. And then v will equal t. So I'll rewrite my f of x using this. F of x will equal f of a plus, I'm going to replace that integral with uv. So I'll have t times f prime of t. That'll go from a to x. And then you subtract this part, minus the integral from a to x, t times f double prime of t dt. Now let me go ahead and plug in these limits into that part. That's going to equal f of a plus, if I plug x in here, I'll get x times f prime of x. And I plug in a, I'll get minus a f prime of a. And then I'll have minus, I'm going to leave this integral here for a moment while I do some other stuff. A to x t f double prime of t dt. Now I'm going to add and subtract something here. What I'm going to put here is I'm going to put plus x times f prime of a minus x times f prime of a, and then I'll have minus a times f prime of a minus that integral. So let me do some cleaning up. That's a little trick. There's only one little trick like that. The rest of it will go pretty smooth. But even so, that kind of stuff is done all the time. Perhaps it's not so incredibly infuriating. The reason I did such a trick is what I wanted to do was take this x times f prime of a and put it with this a times f prime of a. So the reason why, let me take this guy here and link it to this guy here, including the minus sign, to get, for this part here then, notice they both have f prime of a in common. So that's what those two get together. Now this piece and this piece, let me move it over. And then minus the integral. And what I'm going to do is this part right here, I'm going to factor out an x. Okay. Notice here, I can replace this piece in here with an integral. See if you can see this. The variable of integration doesn't matter, so I might as well make it agree with the other one. If you notice, when I take the integral of f double prime, I'll get f prime. You'll plug in x, f prime of x, and then you'll subtract plugging in a. So there it is, and there's the x. And then over here, if you'll notice, these both are integrals over the same interval. And notice the variable of integration is t. That means since x is not involved in the integration, this integral thinks that x is a constant. In fact, it thinks it's a b. It doesn't matter. It thinks it's a constant. So I can actually take this x and bring it inside of the integral. Now, what I'm going to do is combine these integrals because they're both, according to dt, same interval and everything. So I'll combine it into one integral, and I will get f of a plus f prime of a times x minus a plus the integral from a to x. Notice they both have f double prime of t in common, so I can write this as f double prime of t times x minus t dt. This is a little complicated for students because right here, this x, think of it as a number because you're integrating with respect to t. And this, of course, was equal to f of x. Now I'm going to do the same game I did before, and I'm going to use integration by parts. So integration by parts again. And here I'm going to let u be the f double prime. Du will equal f triple prime of t dt, and then dv will equal the x minus t portion. When you integrate that, remember x is supposed to be a number. So when you integrate this, if you let your w equal x minus t, then your dw will be negative 1. X will zero out, but t, the derivative of t, will be 1. So this is like w to the first power. dw is negative 1. When I take and integrate it then, I will get negative x minus t squared over 2. So let me come back here for my f of x. Let me put my f of a back, plus f prime of a times x minus a, plus, now let's put the uv together, so it'll be a minus actually, minus f double prime of t over 2 times x minus t squared. That'll go from a to x. And then when you subtract this, the minus will make it a positive sign. So I'll get plus the integral from a to x, f triple prime of t over 2 times x minus t squared dt. I'm not really sure where I want to put this 2, but it's not that big of a deal. Let me go ahead and throw in my x and my a's into this thing. So this equals f of a. I'll try to make my font a little bit smaller so I can get it all on one screen. So when I plug x into this, that means I'll put an x wherever t is. And then when I subtract the negative, I'll get a plus, and I'll plug in a. And then I will leave this integral there. All right, one more time. I'm going to use integration by parts again. Where I'm going to let u be, hopefully you've guessed it by now, f triple prime of t. Du will equal f to the fourth of t dt. And then dv will equal x minus t squared over 2 dt. And then when you integrate, once again, let w equal x minus t. dw will be -1, and you'll end up with negative x minus t cubed over 6. That'll be 3 times 2. So then I can rewrite this again, see how much I can get on one page. Let's go there. This will equal f of a plus f prime of a times x minus a minus f. Now notice here, x minus x is 0, so that cancels. That's just zeros out. But you'll have this part still. So now let's go ahead and have my uv. I'll put these two together again, so I'll get f triple prime of t, and it'll be minus, I forgot that again, minus f triple prime of t times x minus t to the third over 6 from a to x, and once again plus this integral, plus, I don't know where to put that 6, but the integral from a to x, f to the fourth of t all over 6 times x minus t cubed dt. As before, let me plug in the x and the a. Let me scooch back a little bit here, and I will get f of a plus f prime of a times x minus a plus f double prime of a over 2 times x minus a squared. I will leave this to you. When you plug in x, you'll get x minus x, it'll zero out. And then you'll add when you plug in a, and you'll end up with plus f triple prime of a. Instead of the number 6, I'm going to write it as 3 factorial. Instead of the number 2, I'm going to write it as 2 factorial. Plus the integral from a to x, f to the fourth of t all over 3 factorial times x minus t to the third dt. This is equal to f of x. Well, you can see it's starting to build the series. I'm missing a piece here. I'll see if I can sneak it in. Put a plus right in front of that. X minus a cubed. See it? The series is building. Series is building. I'll do the same game again, except now I'll let u be f to the fourth. dv will be x minus t to the third over 3 factorial. When you integrate again, you'll get a 4 factorial. So you can see it is getting to f of x. And in fact, I can rewrite it this way. F of x can equal, now I can do the sum. K equals 0 to infinity. And I can do f to the k, evaluate it a over k factorial times x minus a to the k. I went a little too far here. I need to put an n. Plus the integral from a to x. And I'll have f. Notice this 4 was 1 more than the highest power. So If n was the highest power I'd have here, then I would have n plus 1 of t. Notice that 3 is 1 less than 4, so I'll have n factorial times x minus t, and 3 agrees with that exponent. So I'll have an n there, dt. So you can see, right here is the Taylor polynomial of degree n, or of order n. There's my Pnx. And if you've been reading the book, I haven't made a lot of mention of this just yet. But this part over here is called the remainder. So Pnx, we've seen that before. And this piece over here is the remainder. Now I need for this, if this remainder goes to 0 as n goes to infinity, then I'll have an infinite series that equals f of x. And that's not so hard. Watch. I'll have f of x equals, let's put the series in there. Let's do the limit as n goes to infinity. The limit as n goes to infinity of f of x will be f of x because there's no n involved in it. So it'll be p sub n of x plus r sub n of x. That'll be the limit as n goes to infinity, summation k equals 0 to n, f to the k, evaluated a over k factorial, times x minus a to the k, plus now with this integral what I'm going to do is I'm going to bring the 1 over n factorial out. A to x, f to the n plus 1 of t times x minus t to the n dt. There's some things, I don't know if I've mentioned it or not, but as n goes to infinity, as long as this is some sort of a bounded, it actually doesn't have to be bounded. If I take x to the n over n factorial and take it to infinity, that always equals 0. I don't know if I've covered that one, but I'll do the limit. As n goes to infinity, x to the n over n factorial always equals 0. So somehow you'll get this and this involved to get that. So what that means is that n goes to infinity, I am going to get the sum from k equals 0 to infinity, f to the k of a all over k factorial times x minus a to the k, plus this part will be 0. So with that then, we will have f of x actually does equal this series. So they are identically equal, as long as x is operating in an interval about a where the function is differentiable infinitely. So all these derivatives exist and are differentiable themselves on some interval about the number a. And by that I mean some common interval for all the derivatives, not an interval for each derivative, but one interval that works for all the derivatives. This part will go to 0. Interestingly enough, there's a formula for this thing. It's called the remainder. It has its own formula. And I thought what the book did here was quite slick. Consider this function here, f to the n plus 1 of t is differentiable on an interval containing the closed interval from a to x. Okay, so if a function is differentiable, remember it's also continuous. So thus, f to the n plus 1 of t is continuous on that closed interval. Therefore, f to the n plus 1 of t is bounded on that closed interval. All this stuff is from Calc 1. So, let little m be the minimum of f to the n plus 1 of t on ax, and let capital M be the maximum. This means that f to the n plus 1 of t is less than or equal to capital M, but greater than or equal to little m for t in the interval from a to x. Right, so what that means is go back to the integral r sub n of x equals this integral from a to x. Remember, it was f to the n plus 1 of t all over n factorial times x minus t to the n dt. Now, since this function here is between m and m, we have this m times the integral from a to x of x minus t to the n over n factorial dt is less than or equal to the integral from a to x f to the n plus 1 of t all over n factorial times x minus t to the n dt, and that is less than or equal to capital M, the integral from a to the x of x minus t to the n over n factorial dt. Now, there's some things I want to say here. For one thing, if this integral happens to be 0, then both sides would be 0 and force the whole integral to be 0. So I don't want to talk about integral being 0. So the integral is not 0. So what I'm going to do is divide everything by this integral. That's why I said, the 0 case can be handled separately. So we're not assuming any kind of 0 here. And that means I can cancel these integrals on the outsides. And we then have m is less than or equal to the integral from a to x f to the n plus 1 of t all over n factorial times x minus t to the n dt, which is less than or equal to m, all over the integral from a to the x of x minus t to the n over n factorial dt. Now, this whole thing, or assuming x is given to us, this whole thing is a number. If x is given, this is a number. This is a number between little m and big M. So I'll just say a number. It doesn't matter. There's a theorem in Calc 1 that says by the intermediate value theorem, so remember, little m was a bound for f to the n plus 1. Big M was a bound for the f to the n plus 1. Both of these were bounds for f to the n plus 1. So here's a number that is between the lowest and the highest values for f to the n plus 1. By the intermediate value theorem, it says f to the n plus 1 will assume every value between m and n on the interval from x to a. So, if there's a value between m and n, there is a number, c. And remember, a is less than c is less than x with f to the n plus 1 of c equals this number here. So now I'm going to multiply it through by that. This is the key to the whole thing right here. This there exists a c. Intermediate value theorem, look back to Calc 1 for what that was all about. I'm going to multiply through by this integral then, and I will get f to the n plus 1 of c times the integral from a to the x, x minus t, all over n factorial dt. And that equals this integral. Now, you may remember that this thing here is the remainder. In fact, they call it the integral version of the remainder. Over here, I forgot an n, but now this is an easy integration right now. If I integrate this where u is x minus t, then du is negative 1, and so I'll get x minus t to the n plus 1. And when I put the n plus 1 down here, I'll get n plus 1 factorial. So this will be f to the n plus 1 of c. This stuff's on the outside. If you don't mind, I'm going to put the n plus 1 factorial underneath of it. And then I will be dealing with negative x minus t to the n from a to x. So I get f to the n plus 1 of c all over n plus 1 factorial. Plug in x, it'll zero out, but then you can plug in a and it'll become positive. It'll be to the, I think I made a mistake here, didn't I? When I integrate, it should be n plus 1, not n. So I'll get to the n plus 1. And that is the remainder. And this is often called this is the version of the remainder that you've seen if you've been reading the book. I haven't really discussed it much, and this is the same kind of thing before. As n goes to infinity, this is like x to the n plus 1 over n plus 1 factorial. It will go to 0. So that will once again prove that the series actually equals the function that it's built upon. And this marks the end of our power series topics.